Okay, so the last topic would be polynomial hierarchy in bounded arithmetic. So here we adopted the convention by Samuel Bass. So this is his method to develop this bounded arithmetic. So we will add two additional symbols into the language of arithmetic. The length symbol and the smash symbol. So length means the length of x, which is the floor of log x with base 2, which means the length of the binary repetition of x. And the second one is the smash function. We define it as 2 to the length of x times the length of y. And here's some definition. So we will have a final structure of the bounded quantifier here. We shall distinguish two kinds of bounded quantifier. So the first one would be called sharply bounded. If it is in the form of this form, for any x less than the length of some term of y. So here I can see that because of this length function here, the upper bound will be very small. So you can think of this this quantifier does not increase the complexity too much, and you can think of this bounded quantifier as kind of you can some kind of ignore this kind of sharply bounded quantifier. And similar to how we define the delta zero subset of natural number in arithmetical hierarchy, we define it as sigma 0b formula as a set of bounded quantifier. But here we only allow bounded quantifiers that are sharply bounded. And we can define sigma nb pi nb similar to sigma and pi formula. But instead of using an alternate unbounded quantifier, we replace the unbounded quantifier by a bounded quantifier, or maybe non-sharply bounded quantifier. So here's the correspondence. So here is arithmetic, and here is bounded arithmetic. And here we have unbounded quantifier. This corresponds to non-sharply bounded quantifier. And here is bounded quantifier. Oh, sorry. And here is sharply bounded. And here are some comments. The first one, it says that because we have additional symbol, smash symbol here, is x less than some term of y if and only if the length of x is bounded by some polynomial in the length of y. So let's say, for example, x less than y smash y, which is 2 to the length of y square. And actually, if we take the length function of both sides, we get the length of x is less than the length of y squared. So you can see that roughly this, if x is bounded by some term in y, if and only if the length of x is bounded by some polynomial in the length of y, and without such this smash function p, it will become linear. So this p is roughly this. No, this smash function is roughly the function x to the log x. So we just add a new function symbol to describe this function. And here's a p here. And actually, with some effort, this is a non-trivial result. The sigma nb definable set of natural number and pi and b respectively is just the complexity class sigma and p and pi and b. So this is the original goal when they define this bounded arithmetic. We add some symbol, then we get some good description of the polynomial hierarchy. But we do not know whether this polynomial hierarchy collapses or not. And next, we shall define the weak system of arithmetic parallel to what we've seen, like I sigma n or p sigma n, and present some connection between them and the complexity theory. But here we do not have any proof because these are deeply this involves too much proof theory and is beyond my talk. So here's the bounded induction scheme. So it's still some induction scheme, but here we restrict it to the level below delta zero. So it's still the same procedure. We have the induction scheme and we restrict it to certain class of formula. So let this T2I is the induction scheme restricted to all the sigma IB formula. And here is something different here. Here we have this S2I is the following. So it says that if phi 0 is true, and if this induction hypothesis is true, then for any x phi x. So here what does it mean? So let's say, for example, x is 11011. This is x, the binary representation of x. Then x divided by 2 floor is 1101. So this thing says that if we remove one bit, we can say that this thing is true. Then this thing is true. So it's something like the induction for binary string on the length of binary string. So it's something like 1101 implies 11011, and also 11010, and so on. If we have this kind of induction, then we know that for any x phi x is true. So this is another kind of induction, but actually we can show that it is weaker than the original form. And also we can have this kind of negation. T2I plus 1 implies S2I plus 1, and then imply T2I, but we do not know whether this is strict. And we can define T2 is the union of all the T2I, and S2 is the union of all the S2I. So here is the bounded induction scheme. And we shall show that this is a good system to develop all the machinery for analyzing the polynomial hierarchy, and also to build some connection between this bounded induction scheme and the computational complexity theory. So I shall grab some result here, but without proof. So the first one says that the polynomial hierarchy is probably collapsed in S2. So in S2, it proves that PH collapse if and only if S2 is finitely axiomatizable, which means that there is finitely many formulas which characterize this S2. So this is the first result. It is by Samuel Bass. And the second one is we have here is NP, and here is co-NP, and we have NP intersect co-NP, which contains P, but we do not know whether the inverse is true. But he shows that if we can prove in some weak system S21 such that some language, so S21 proves that some language L is in NP and L is co-NP, then implies that L is actually in P. So formally says that the class of sigma 1 formula, which is probable equivalent to the pi 1 formula, is exactly the polynomial class. So these are the two results between bounded arithmetic and complexity theory. But I will not present the proof because it's too deep for me and I cannot understand it. And also, there are some other connection between logic and complexity theory. So that's another branch, which is called the proof complexity, which is called the propositional proof complexity. Propositional proof complexity. So here we have lots of propositional proof system, and we will show that to prove a theorem in propositional logic, how much complexity we need to use, and the proof of and the length of the proof, we have some upper bound and lower bound, and etc. So that's another line of research which has connection between between logic and complexity theory. So that's all for my presentation for this three topic, and thank you for listening.